This is the solution to example 7 from the P.3 and P.4 notes. So binomials, those are polynomials with two terms, can sometimes be factored as the difference of two squares. Those are two perfect squares. In the previous section, we learned that if we have the product of the quantity x plus y times the quantity x minus y, that multiplies out to be what we call a difference of squares, which would be x squared minus y squared. We can use this pattern to factor some binomials. So we can only factor binomials. We could always take out a greatest common factor, but with that exception, we can only factor them if it is a difference of squares. Otherwise, they're not going to factor. So in this first example, we have x squared minus 49. This is a nice difference of square pattern. What are we looking for? The first term is a perfect square. The second term is a perfect square. So this is x squared minus 7 squared. I do not expect you to do this step. I'm just doing it now so that we can explicitly see the pattern. This will factor as x plus 7 times x minus 7. We're simply taking the square root of each of the two perfect squares. Let's look at 36y squared minus x to the 10th. This is a little bit harder difference of squares factoring problem, but we can think of 36y squared. That's still a perfect square. It's 6y squared, and x to the 10th is also a perfect square. It's x to the 5th squared. And now using the pattern, x plus y times x minus y is x squared minus y squared. Here, we can factor this as 6y plus x to the 5th times 6y minus x to the 5th. Let's turn the page, and we will look at some more problems where we can factor using difference of squares. But here, sometimes there's a common factor, greatest common factor, and that'll make it so that it doesn't look like a difference of squares. But if we always think about taking out the GCF first, then sometimes we can see the hidden difference of squares pattern that's there. So here we have the expression 125x squared minus 80. This is two terms. It's a binomial. It doesn't appear to be a difference of squares initially, but let's take out the GCF. So the greatest common factor between 125 and 80 is 5. That will leave us with 25x squared minus 16. And now we can see that indeed we do have a difference of squares because 25x squared is 5x squared and 16 is 4 squared. So now we can see explicitly the difference of squares pattern. So this will multiply out as 5 times factoring the difference of squares. We have 5x plus 4 times 5x minus 4. Let's look at the next one. Okay, in this next problem, it might be tempting to multiply everything out, multiply out the x minus 5 squared, combine like terms, and then factor. But here we can be clever and we can recognize that this is really a difference of squares because we have the quantity x minus 5 squared and 16, which is 4 squared. So this is actually 4 squared. So we can factor this as a difference of squares. So this would be x minus 5 minus 4 times x minus 5 plus 4. Now we can simplify within the parentheses, so that will give us x minus 9. And negative 5 plus 4 is minus 1 times x minus 1. Now, if you actually multiply this out, you can, and I'll do that here as well. So x minus 5 squared is a square of binomial. This will become a perfect square trinomial when we multiply it out. So this is going to multiply out as x squared minus 2 times 5 times x. So it's going to be minus 10x plus 25 minus 16. And simplifying this, we'd get x squared minus 10x plus 9, which we then need to go ahead and factor. And we haven't talked about how to factor trinomials, but we will in a second. We're looking for two numbers that multiply to 9 but add to negative 10. And that will give us x minus 9 times x minus 1. So I think it's a little bit easier if we recognize the difference of squares pattern in that example. We're going to go on to example E. So here we actually do have a perfect squared. So 81m to the fourth is 9m squared squared. And 1 can be thought of as 1 squared. So now using the difference of squares pattern, we can factor this as 9m squared minus 1 times 9m squared plus 1. But we have to remember to always factor completely, which means we're going to look at each of our factors and see if it can be factored further. So 9m squared plus 1 is the sum of squares. That will not factor, but 9m squared minus 1, this is actually another difference of squares, so we can factor again. So let's continue factoring this. 9m squared minus 1 is 3m squared minus 1 squared. And then we have 9m squared plus 1. And then the difference of squares will factor as 3m plus 1 times 3m minus 1 times 9m squared plus 1.